Good afternoon, everyone. Today we will see the topic having a name complex number. Now, how we define the complex number? When x and y are real, then the number which is expressed in the form of x plus iy is called complex number. That complex number x plus iy is generally denoted by the letter z, and therefore we can write z is equals to x plus iy. Here the x is called real part of z and that y is called as imaginary part of z, and that x is represented by the symbol that is re of z, that is real part of z, and that y is represented by that symbol I am of z, that is imaginary part of that z. And here I is equals to the value of that I in that complex number is equals to root of minus 1. If z is equals to x plus iy is the complex number, then z bar is equals to x minus iy is called the conjugate of that complex number z, and it is denoted by z bar. Next we see some properties of the complex number. Let x1, y1, x2, y2 belong to R, where R is the set of real number. Let z1 is equals to x1 plus iy1 and z2 is equals to x2 plus iy2 with two complex number. These two complex numbers are equal if and only if its real and imaginary parts are equal. That is, we can say that if z1 and z2 both are equal, then x1 is equals to x2 and y1 is equals to y2. Again, second property, if two complex numbers are equal, then its corresponding conjugates are also equal. That is, if z1 is equals to z2, then we say that z1 bar is equals to z2 bar. Next is a addition, subtraction, multiplication and division of complex number is also complex number. We see first addition of two complex number. Here we consider two complex numbers z1 plus z2. z1 is x1 plus iy1 plus z2 is x2 plus iy2. Now from that term we collect the term of real terms and imaginary terms. Here the real terms are x1 x2, so we write x1 plus x2 plus I take a common from the last two terms, and here is a y1 plus y2. Again if we see that number, that is again a complex number, and therefore addition of two complex number is a complex number. Next is a z1 minus z2, that is x1 plus iy1 minus x2 plus iy2. Again collecting the real and imaginary part, so we can write in the next line x1 minus x2 plus I take a common from that last two term, here is remaining y1 minus y2, and again this is nothing but a complex number. Then we see the product of two complex numbers z1 into z2, that is x1 plus iy1 into x2 plus iy2. When we take a product, that is x1 into x2 plus x1 into iy2 plus iy1 into x2 and plus I into I, it become I square into y1 y2, and then we collect the real and imaginary part. The real part is the without term of I, so we take x1 x2 plus here I take a common and remaining x1 y2 plus x2 y1, and last term is a I square. As we know I is a root of minus 1, so that I square is equals to minus 1, and therefore here the plus sign is replaced by minus, so we can write minus y1 y2. Again x1 x2, that last term minus y1 y2 plus the middle term I into x1 y2 plus x2 y2, and again we get the complex number, and therefore product of two complex number is again a complex number. Next is a division, z1 upon z2, in numerator x1 plus iy1, in denominator x2 plus iy2. Now to convert it in the form of complex number, we have to multiply by the conjugate of denominator and divide by also that conjugate. Now here the that denominator is x2 plus iy2 and its conjugate is x2 minus iy2, so we take a multiplication of that x2 minus iy2 in numerator as well as in denominator. So finally again we take the product of that two terms in numerator, x1 plus iy1 into x2 minus iy2. So we get x1 x2 plus y1 y2 plus, I get a common here, x2 y1 minus x1 y2, and in denominator it is in the form of a plus b into a minus b. So finally we take a square minus of I square y square, but again we know that I square is a minus, and finally we get minus minus plus, so it can be written as x square x2 square plus y2 square. And we separate the real and imaginary part by separating the denominator, and again that number is converted in the form of complex number. Next we see the polar form of the complex number. If the complex number is represented by z is equals to x plus iy, then its polar form is r into in bracket cos theta plus I sin theta. That implies x is equals to r cos theta and y is equals to r sin theta. When that two terms we square and add, so what we get? We get x square plus y square is equals to r square, and in bracket cos square theta plus sin square theta. But that cos square theta plus sin square theta is nothing but a 1, and therefore finally we get x square plus y square is equals to r square. So we write in this way, that is r square is equals to x square plus y square. When we take a square root on both sides, so we get r is equals to under root of x square plus y square. That r is called as a modulus of z. It is called as modulus of z, where that z is a complex number, and it is denoted by the symbol, that is z is in between two vertical line, that is called as a mod of z, and therefore mod of z is equals to under root of x square plus y square. Now on dividing y by x, so what we get, that is y by x is equals to, here y by x is equals to r sin theta upon r cos theta when we put the values of y and x. Again r get cancel, and finally we get sin theta upon cos theta, so that is a tan theta, and therefore we get tan theta it is equals to y by x. And from that we get the value of theta, that is nothing but theta is equals to tan inverse of y by x. That theta is equals to tan inverse of y by x is called as the amplitude or argument of z. Again it is denoted by amp of z or arg of z, and therefore amplitude of z is equals to tan inverse of y by x. So in this way we see the polar form of that complex number. Next we see the De Moivre's theorem, and because we have the applications of that De Moivre's theorem to find the power of complex number. Now what is the statement of De Moivre's theorem? If n is an integer or fraction, positive or negative, then one of the value of cos theta plus I sin theta raised to n is equals to cos n theta plus I sin n theta. So that is the statement of De Moivre's theorem. Now one result we have to remember here, that cos theta 1 plus I sin theta 1 into cos theta 2 plus I sin theta 2, that can be expressed as cos of theta 1, that angle, plus that angle, that is cos of theta 1 plus theta 2 plus I into sine of again that angle of first bracket theta 1 plus second bracket angle, that is theta 2, and therefore it can be written in this form, that is cos of theta 1 plus theta 2 plus I into sine of theta 1 plus theta 2. If there is a product of three terms in this way, that is cos of theta 1 plus I sin theta 1 into cos of theta 2 plus I sin theta 2 cos of theta 3 plus I sin theta 3, then it can be written in the form of cos of theta 1 plus theta 2 plus theta 3 plus I into sine of theta 1 plus theta 2 plus theta 3. And in this way we can take the product of 3 terms, 4 terms, 5 terms, and so on. That result is applicable to solve some problems, and that's why we write that result here. Now when we solve one problem by using a De Moivre's theorem, what we have to do here, we have to simplify that term, that is cos 3 theta plus I sin theta raised to 4 into cos 4 theta minus I sin 4 theta raised to 5 cos 4 upon cos 4 theta plus I sin 4 theta raised to 3 cos of 5 theta plus I sin 5 theta raised to minus 4. Now first we write down that term as it is, that is cos of 3 theta plus I sin 3 theta raised to 4. Second is a cos 4 theta minus I sin 4 theta raised to 5 denominator cos of 4 theta plus I sin 4 theta raised to 3. And last term is a cos 5 theta plus I sin 5 theta raised to minus 4. And now we consider the one by one term. Now first term is a cos of 3 theta plus I sin 3 theta raised to the power 4. Now by the De Moivre's theorem, how we can write that result? By De Moivre's theorem, how we write that term? That is a cos of 3 theta plus I sin 3 theta raised to 4 can be written as cos of that angle can be multiplied by that angle here. So 3 theta into 4. So it become a cos of 4 into 3 theta plus I into sin of 4 into 3 theta. And therefore it can be written as cos of 4 into 3. It become a 12 theta plus I sin 12 theta. So that result is also applicable to another term. So we write one by one term, remaining term cos 4 theta minus I into sin of 4 theta raised to 5. It can be written as cos of 5 into 4 theta minus I into sin of 5 into 4 theta. Now that is 5 into 4, it become a 20. So we can write cos of 20 theta minus I into sin of 20 theta. Next term in denominator, that is cos 4 theta plus I sin 4 theta raised to 3. So directly I can write, when we multiply by 3 to 4, it become a 12. So directly we can write cos 12 theta plus I sin 12 theta. And last term cos of 5 theta minus plus I sin 5 theta raised to minus 4. Now when we multiply by minus 4 to that angle, so it can be written as cos of minus 4 into 5, that is a minus 20 theta plus I into sin of minus 20 theta. Now as we have the result as cos theta plus I sin theta is equals to e raised to the power I theta, and cos theta minus I sin theta is equals to e raised to minus I theta. So we write, we use that result for the above term, and therefore it can be written as cos of 12 theta plus I sin 12 theta is equals to e raised to the power I 12 theta. Then next is a cos of 20 theta. Here is a minus sign, so it can be written cos of 20 theta minus I into sin of 20 theta. It is equals to, as there is a minus sign, so it can be written minus of I 20 theta. Then the next cos of 12 theta plus I sin 12 theta is equals to e raised to the power I 12 theta. Then last term, as there is a minus 20 theta and cos of, we know that cos of minus theta is equals to cos theta, and sin of minus theta is equals to minus sin theta. So that term can be written as cos of 20 theta minus of I into sin of 20 theta. And again there is a minus sign, so it can be written as e raised to the power minus of I 20 theta. Now if we consider that term, so we write the here LHS, that LHS is equals to, now we have to put the values of that each term here. Now if you consider the first term cos 3 theta plus I sin theta raised to the power 4, that is nothing but the cos 12 theta plus I sin 12 theta, and that cos 12 theta plus I sin 12 theta can be written in this form. So we write that term as e raised to the power I 12 theta. Then next term cos of 4 theta minus I sin 4 theta raised to power 5, that is cos 4 theta minus I sin 4 theta raised to 5 is equals to cos 20 theta minus I sin 20 theta, and that cos 20 theta minus I sin 20 theta is nothing but e raised to the power minus I 20 theta. Now we consider the term of denominator. Here is a cos 4 theta plus I sin 4 theta raised to 3, and that term can be written in the form of cos 12 theta plus I sin 12 theta. Again cos 12 theta plus I sin 12 theta is nothing but e raised to the power I 12 theta. In the second term, cos of 5 theta plus I sin 5 theta raised to minus 4, that can be written in this form cos of minus 20 theta plus I sin minus 20 theta, and that cos of minus 20 theta is nothing but cos 20 theta, and sin minus 20 theta is a minus sin 20 theta, and therefore we write cos 20 theta minus I sin 20 theta, that is nothing but e raised to the power minus I 20 theta. Now as we see, both the terms of numerator and denominator are equal, so what we get finally here in numerator, that is e raised to the power, that both the here that term get cancelled, that term get cancelled, and finally what we get, that is equals to 1, and therefore after the simplification, that LHS is equals to, we say that is equals to 5. In this way we solve that problem by the use of De Moivre's theorem. Thank you.